I can hear you. Okay, so let us start. So now that the the list of selected candidates has been declared, we would like to organize this remaining lectures in slightly different way. Because I think INMO is on 15th January, so we have exactly 6 weeks before that. So for the most part, I would like to focus on the problem solving that is relevant to INMO, and that the best way to do that is to look at the past INMO question papers, as well as few INMO practice papers which people have designed from time to time. So now, for example, today what I'm going to do is we are going to look at functional equations, but instead of trying to look at other problems, we can look at INMO past papers and just the functional equation problems out of that. So in that way, now I think it's a good idea to just to go topic wise and theme wise, so that we make sure we cover all the various ideas that are involved in solving an INMO problem. So we will do that in the next few weeks. But meanwhile, because this would be kind of advanced content, so students who are not qualified for INMO, of course, they are also welcome to listen to this. But in addition, they should also be doing some pre-RMO kind of practice. So how to enable both these things together? So one way is that I already have been designing some problem sets and uploading them on a website where you can actually browse them week at a time and go back and solve them. So, okay, so I will share the link with you later on. But anybody who wants to practice for IOQM, there are like week by week question problem sets. Already this is like week 4, so you can go back and start from the first week and solve all the 6 problems from there. And every week you will keep getting new problems here. So you will always be able to get some fresh practice material that way. Okay. So this is what I will recommend for those who are practicing for PRMO. Okay. But in addition, of course, in the actual lectures, we will be talking more about INMO level topics. So, I mean, as such, the difficulty level of INMO, or rather the kind of meta is what we can call it, of what are the typical problems that come, that keeps changing from year to year. But there are some common themes which are quite recurring basically, and so those are important for all of us to be aware of. So, for example, one thing I already indicated some time ago is the idea of periodic valuation, because that has become sort of more and more popular these years on in problem solving. So, in the same, actually, functional equation was more popular in the previous year's paper. These years, I don't know if we get those many problems, but still, it's a good topic to understand how to solve. Okay, so that's why I'm going to start with functional equation. It's a really good topic to understand, and it also has broader implications in terms of your future development. Because of course functions are one of the most important topics that we can think about. But even going further in lot of engineering context, what you're really doing is solving a functional equation in some sense. Okay, like for example, if you are in charge of designing the traffic signal at an intersection, then what should be the function that controls when the signal turns red to green, so that you reach some objective. Maybe the objective is to maximize the throughput of how many cars can pass through that intersection or something like that. So you'll find the concepts of functional equations very general and common to all domains that you will be studying. So that is why I think it's a good idea to start with functional equations. So last time we already started with one problem. So that was from the previous week's problem set. So we will complete that also today. And for those who were not able to join that meeting, you should go back and watch that the last question, how we started to solve that. But I'm just going to go back and talk again a little bit more about the sort of the theory part of what is a functional equation. So I mean, to begin with, we also briefly talked about last time what is a function. So function which goes from one set to the other set, right? And we define that as a subset of the cross product. So essentially f is nothing but a subset of a cross b with certain rules that we explained last time, that basically for every element in a there has to be a unique pair which belongs to this cross product. So with that definition, the thing which I have to highlight again is that when you are given a problem, find all functions which satisfy some rule, there is no prior assumption that it's a well-behaved function. Okay, so well-behaved means that there is some nice formula or expression which will describe the function. That is a luxury. I mean, if we can prove that that is the case, then we know. But otherwise, we cannot assume that directly that it's a nice function. So we have to start with the most general assumption about the function. And so if some domain is given, like if A is, let's say, the set of natural numbers. Okay, so in the simplest case, maybe f could be a function from n to n. Okay, so the condition which I said that f need not be well behaved, which means that f of 1, f of 2, f of 3, and any f of n for any natural number n can be assigned completely arbitrarily. There is no need for there be any connection between any of these values. Okay, so defining a function does not put any conditions, but then you are given some special clause. So for example, the most simplest function you can imagine is what we call a linear function. Suppose you are given that f of m plus n is equal to f of m plus f of n. Okay, so for all natural numbers, suppose this condition is given, so this kind of function is what we call an additive function. Okay, and as I also mentioned last time, what this is really is you can think of this as infinitely many unknown variables and infinitely many simultaneous equations, because with this information you can write all equations, right? F of 1 plus f of 1 equal to f of 2, etc. all the way, any two numbers you can choose, you will get one equation. So this is just simultaneous equation with infinite unknowns and infinite equations. That is one way to think about functional equations. And now what we need to start doing to solve this functional equation, which means we have to find the function f which satisfies this particular rule. So by adding, like, trying small experiments, and you can start to see the pattern and then try to make a guess that what this function can look like, and then that will be your solution set. So not necessarily that there will be only one function which satisfies this rule, but as many functions are there, we have to find all of them. Okay, so in this case, for example, the important thing is choosing which equation you write, because obviously there are infinitely many equations and you cannot write all of them. So which of the equations will give you some useful information which we need to write. So for example, f of 1 plus f of 1 equal to f of 2. So which clearly means twice f of 1 is equal to f of 2. So what does directly show that f of 1 and f of 2 related? So the previous, without this information, f of 1 and f of 2 can be chosen completely independently, right? Nothing stops you from setting f of 1 is 20 and f of 2 is some 1 crore or some very big number. But now that this condition is there, still there is a degree of freedom, because we can choose, for example, f of 1 as 4 and f of 2 as 8 or something like that. But now at least f of 1 and f of 2 are related in some way. So that is progress for us. So in the same way, you have to try to keep relating various numbers and try to collapse everything into as few independent variables as possible. So can you suggest what should be the next step for us?
So on both sides, add f of 1.
Yeah, so if we add f of 1 to both sides, so on the left hand side we'll get 3 times f of 1, and on the right hand side we'll get f of 2 plus f of 1, and again we can invoke the given information to say that that is f of 3. Okay, so 3 times f of 1 is equal to f of 3. So which means that f of 1 and f of 3 are also related now. And now, I mean, it's not very hard to see what is the pattern which you can prove by induction, that in general for any natural number n, you'll see that n times f of 1 is equal to f of n. Okay. So which means that actually, if you think about it, basically, once you decide what is the value of f of 1, all the other values will be uniquely assigned, right? And that is one thing, and also the other part is that you are free to choose any value for f of 1, because we can verify that let f of 1 be equal to k, where k can be any natural number of your choice. And then if we define the function as f of n is equal to n times k, and we can check that this definition satisfies the given condition, this f of m plus f of n is satisfied by this definition. So therefore, so you see in this problem also, we don't have a unique solution for the function f. We have in fact a whole family of possible functions. So for example, f of n can be n for all n, f of n can be 2n for all n, 3n for all n. So any multiple of n, of course that the factor has to be constant. Okay, so all of these are valid solutions of your problem. Okay. So we have an infinite solution set actually here. Okay, so basically we have shown two-way street basically, that if I have a function which satisfies this particular condition, then it has to be of the form n times f of 1. And reverse, if you take a function which is of the form n times f of 1, it will satisfy this equation. So you completed sort of both directions of the calculation. Okay, so this is like the simplest typical example that is given to illustrate what is a functional equation. Okay, and in the same spirit, you can think of other variations. Now, for example, if I just change the question slightly, now let's say we are not talking about additive functions, we are talking about multiplicative functions. So same domain, let's say f goes from n to n, and now the condition is f of n is equal to f of mn for all positive numbers, natural numbers mn. So if this is the condition now, now can you think about how you start approaching this problem and how to find all the functions which satisfy this?
Sir, we can put m is equal to 0 maybe.
We are talking natural
Oh,
number.
yes, sir. Sir, m is equal to 1.
Yes. So I mean, just like a detective looking for clues, right? We have to start sort of finding out these clues by substituting some special values. So let's say if we put n is equal to 1, we get f of 1, m times f of 1 is equal to f of m. And now since everything is non-zero, we can cancel f of m from both sides and we get f of 1 is equal to 1. Okay, so that is at least we obtain f of 1. Okay. So now let us look at f of 2. In the previous problem, because we have addition, so it was easy to relate f of 1 to f of 2. But now it's not that simple. So using this equation, what can we possibly relate f of 2 with?
f of
I
4.
mean, f of 4, correct? Because I can put m and n both as 2. So I'll get f of 2 square is equal to f of 4. And now in the same way as what we did before, you can think about what happens if I keep going down this line. So I can keep multiplying both sides by f of 2, right? So if I multiply both sides by f of 2, I'll get f of 2 cube is equal to f of 8. And so in this way, what is the most general statement that we can make?
F of 2 raised to n whole square is f of
F
or
of
f of 2 whole raised to n is equal
yeah,
to f of 2 raised to n.
correct. So f of 2 whole raised to n is equal to f of 2 raised to n. And now if you think about it, there was nothing special about the number 2 in this. It could be replaced by any other number, right? Because basically what we are saying is that, I mean, any natural number f of m times f of m, let's say this is occurring n times. Then one term at a time, we can combine them, and basically this will be equal to f of m raised to n, right? So this is true for all natural numbers. It doesn't matter. So with this information now, are we equipped to try to define what will this functional equation look like? And I mean, clearly there is a really large degree of freedom available to us, because, for example, f of 2 can be chosen independently from this example. So basically, which values can be chosen independently and which cannot be chosen independently? What is your intuition about that?
Prime numbers.
Yes, correct, prime numbers. Because now basically we have seen how to compose any number into its power. And one more important thing to note is that you cannot, I mean, there is no way from f of 2, no matter how many times you substitute, to get something about f of 3 directly. Okay? So there is no direct connection between f of 2 and f of 3 that can be established. So in the same way, basically all the prime numbers can be chosen individually. So f of 2 can be chosen to be some value. Let's say we denote the value of f of 2 by as k2, f of 3 as k3. Similarly, f of any prime number can be denoted by kp, where kp can be any natural number. There is no restriction on that. So if we are defining the values at all the prime numbers like this, and now some new number n is there, and you want to compute f of n. So what would be your procedure to do that? So first we would like to look at the prime factorization of n, right? So let's say n is p1 raised to alpha 1, p2 raised to alpha 2, pr raised to alpha r. Okay, this is the distribution of n. Then f of n will be equal to basically something that you already seen before, that we can, although we didn't write it explicitly, but clearly we can compose this operation into like n products together, right? So f of a1, f of a2, f of ar, any r terms like this can be combined in one step into the product. Okay, so I don't have to do that every time, and the reverse is also true. So therefore, f of n can be written as the f of each of these individual components, right? So f of p1 raised to alpha 1, f of p2 raised to alpha 2, f of pr raised to alpha r. And now these themselves can be using this rule, right? I can pull out the power alpha 1, alpha 2 and write them in terms of f of p1 whole raised to alpha 1, f of p2 whole raised to alpha 2, and f of pr whole raised to alpha r. Okay, so this is possible. And now because we have already decided the values that the function will take at all the prime numbers, so we know that, so f of p1 can be denoted by kp1. So this is kp1 alpha 1, kp2 alpha 2, etc. So this is the value that we can compute for f of n, and it's not very hard to check that a function which is defined in this way, no matter what the values of k1, this k2, k3 are, it will satisfy that original equation, right? F of n is equal to f of n. So this will be satisfied by this kind of function all the time. So this is like actually very big family of like equations, or other solutions to our function equation. Okay, so that is also perfectly valid. That there is no restriction that your function has to be well behaved. So these are some small examples to motivate how we should start thinking about functional equations. And in general, there are few problem solving techniques that are worth keeping in mind, depending on which domain. So a lot of things depend on whether the domain was natural numbers, integers, rational numbers, or real numbers. So you will get some of these, or sometimes some variant of this. So maybe it is like q plus, which is just the positive rational numbers or something like that. But basically, these are the four main domains on which your functions may be operating. And based on the which domain you are operating, your technique can slightly differ. So for example, clearly for integers and natural numbers, one important idea is induction, that you can try to do some kind of induction on these two sets. For rational numbers, also you can use induction, but unless the problem is very specific. I mean, your idea is that if you try to think of a fraction p over q, I mean, doing induction on P is relatively easy. From P, you can relate to P plus 1 by Q at least in some way. But going for induction in the denominator is very hard. So from P to Q plus 1, in almost most cases, that will be very difficult to make this kind of jump. So this is not possible. But can you think of some other approach to apply induction in rational numbers? So for example,
Sir,
we
if we
yes, go ahead.
sir, if we prove that if it is true for P by Q and then it is true for Q by P, then I think we will be.
Yes, correct. Yeah. So we had seen an example of this in the when we did the triangle with angles ratio, right? A equal to K times B. We had seen that kind of idea. So suppose from P by Q, I can prove that find the value of Q by P. Okay. So suppose f of P by Q and f of Q by P are related in some way. Okay. Then that will allow me to what can I do? I mean, if I want to reach any general m by n number, then how can I reach that from this starting point? So,
From
for example, one thing you could do is that, I mean, assuming that f of 1 is known. Okay, so from f of 1, I can reach f of n, and from f of n, I can reach f of 1 by n, and then from f of 1 by n, using the positive induction step, I can reach any number which has a fraction of n, right? So that is one approach certainly. The other approach is, I think, the finite continued fractions, which I mentioned last time. So that is also a valid approach. So either way works, but yeah, basically, in effect, you can also think of applying induction on rational numbers. What about real numbers? Because on real numbers, you obviously cannot apply any of these techniques. So dealing with real numbers is a completely different kind of ballgame, and we will see some examples of that. I don't know if we have time today, but like one very good book which I recommend is very classical book by B.J. Venkatachala. So he has been one of the most important pillars of the mathematics Olympiad movement in our country. So his book for functional equations is a very good reference for a lot of problem solving practice. Uh, Unfortunately, what happens many times in problems which are discussed in this book is that the solution just says something like, let us consider some expression, and that expression seems to come out of nowhere, and that is very I mean, for a student who is trying to solve or trying to figure out how he is supposed to start thinking, that is not very useful. But that is something that you have to spend the time and try to understand on your own, that where did that let us consider come from, because there will be some intuition or some hint or clue in the question which will suggest one particular approach. So with more and more practice, you will start to sort of sniff out those details, that what is the expression or function you need to consider to solve the given problem. Okay. So but definitely would like you to look at this book. Of course, given the time crunch that, I mean, in 6 weeks, so I don't think it will be realistic to solve this book right now in the 6 weeks, but for future reference, that whenever you are free from any exam pressure and you have enough time to spend, this is a really good book for trying this out. Okay. Apart from induction, there is one more important technique, which of course, in a way, we have already been referring to that in number theory, and it is useful here also, which is kind of estimation or bounding. Okay, so estimation or bounding can be useful if that kind of information is given to you. So, for example, maybe in some problem it is given that the function is decreasing or increasing. Okay, so suppose given that some function f of n to n such that f of m is less than f of n if m less than n. Okay, so the function is given to be increasing. So now with this information, suppose you are able to find, let's say f of 2 is equal to 2 and f of 4 is equal to 4. Okay, so now you see that because of these two information, it forces that f of 3 must be 3. There is no choice. So this kind of idea can be useful in some problem. Okay, so estimation is an important concept to keep in mind. Okay. And there are few other smaller techniques which might be useful in particular problems. But there is only one technique which is the most useful across all domains, and that is the one which we always try to think about, which is I don't know if there's a name for this, but we can call it closing the system. closing the system of equation. So what is the meaning of this term closing the system? Basically, as I mentioned at the start, functional equation is basically an infinite number of variables and infinite equations. And we don't have any method to solve infinite variable solution directly this way. But if we can find within that sort of broad loop some small part which is self-contained, okay. So for example, suppose you can find three equations such that they are relating f of, let's say, first equation relates f of 2 to f of 3, second equation relates f of 3 to f of 5, and third equation relates f of 5 to f of. So now we don't have to worry about the infinite equations and infinite unknowns. Now we have three equations and three unknowns, and now we have to just solve that particular system, and we will get the values of all the three variables. So that is what we mean by closing the system. Okay, and we actually saw an example of this in the last week's problem where I forget the details, but basically we had f of 2 was related to f of 4, and we got two equations which relate these two together. So you had two equations and two unknowns, so you can solve it. Okay, so this closing the system is a very important idea, and we should definitely look at some problems which employ this technique. Okay, these are sort of the most broad ideas that we need to know before we start with functional equations actually. But many other smaller ideas we will discover along the way as and how we actually solve the problems. So maybe I'll just go back to last week's problem sheet, and in case anybody who has not solved that problems would like you to take another look at that problem. Okay. Okay, so question 6 was the one which we were doing last time. So in case for those who have not seen last, did not attend or did not see last week's lecture, I'll just give you a few minutes to try and think independently that how you can start approaching this problem based on the ideas that I've discussed today. Okay, so we started to analyze this problem last time by first trying basic values. So important thing is q plus is given to a positive rational, so we don't have access to zero, which can be a bit of a handicap because many times just putting some value as zero will give you some useful information, but we cannot do that here. So you have to look at some other clues. So putting the value of some variable as one is of course one of the most useful ideas. So we did that. Okay, we did. I won't rewrite everything, but we can just refer to last time's notes. Okay. So, so if you look at the screen, okay. So first thing we tried was if you put x and y as one, we get the value of f of one, and that we got f of one as equal to two. Then it's useful to just put one of the variables as one. Don't put x and y to both as one simultaneously. So if you just put one of them as one, like suppose you put y equal to one or x equal to one, you get the equation f of y equal to f of one by y. So which means that the reciprocals of values are related to each other, which is very useful because now we can only think of one half of the number line basically. Then another useful idea is just putting x and y equal to each other. Okay, x equal to y, because then what we get, x f of x y will become f of x square, and basically what you got is the equation like this. So f of x and f of x square are now related to each other. Okay. So this was the idea which led to the first loop, so to say, that how we, as I said, that we would like to obtain f of 2, for example. So we need to find some closed loop which is relating f of 2 to f of 4. So that is where we made use of the second condition given in the problem, right? So far we had only looked at the first equation, but the second equation is more directly, just looking at the equation, do you get some kind of flavor that the first equation is giving you some kind of multiplicative information, because from x you can go to multiples of x, but you cannot add or subtract one. And the second part is giving you the additive kind of information, because here f of x minus 1, f of x plus 1 and f of x are related. So you have to make use of both parts appropriately for whether you want to add or you want to multiply. So now the thing is f of 2 and f of 4 are related to both sequences, right? Because f of 2 square is, of course, 2 square is 4. So there is multiplication. But 2 plus 1 is 3 and 3 plus 1 is 4. So that is addition. So that is how the two values can be rated to through different chains. And that is what we were able to do last time, that if we just plug the value of x equal to 2 and 3 in the second equation, we get one more equation that relates f of 2 and f of 4. So now putting both of those together, we are able to solve the equation. So basically we got this closed system of equations where f of 4 and f of 2 are the only unknown. So we have two equations and two unknowns, and we are able to solve it. And we got the value of f of 4, f of 2 as well as f of 4. And we tried a few more examples like that. So we got f of 3, f of 4. And now looking at these values of f of 1, 2, 3, 4, we can start to develop some guess that what our function might be looking like. And then somebody guessed correctly that x plus 1 by x is the function which satisfies this equation. So now, of course, the important question is that we can substitute x plus 1 by x in the original equations and verify that it satisfies. But that doesn't prove that that is the only solution, right? That only proves that that is one solution. So read the question carefully. It is saying find all functions f. Okay. So if the question were just find one function, then we are done. But we need to prove that no other function can exist. Okay. So in other words, we have to prove that for any rational number q, positive rational q, f of q is equal to q plus 1 by q is forced. Okay. So this is what we would like to prove. And I think this is where we left the problem last time. Okay. So now with this information, how can we proceed? So let me rewrite the original equations which we have to work with. So the original information given to us is that for all x and y, which are positive rationals, f of x, f of y is equal to f of x, y. plus f of x by y. So this is the first equation given to us. And the second equation is x minus 1, f of x minus 1 plus 1 f of x plus 2. Again, this is for all positive. Not all, it's different. So this is the information available to us. And how can we proceed from here now? And what we have found so far is the values of f of 1, f of 2, f of 3, all of those things. So our guess is that f of q is q plus 1 by q. So the first thing we will see that now that we have found f of 1 and f of 2, right? So we know f of 1 is 2 and f of 2 is equal to 5 by 2. So with this two information given to us, which new values can we find? In particular, look at the second equation. Now, what is the nature? Which three values it is relating for the function? X minus 1, x plus 1, and x. So three consecutive values are related to each other. So now can you see that this is kind of a sliding window
Yes, sir.
where
We can get all integers or natural numbers.
all natural numbers, correct? Because if we put x equal to, and that is exactly what we did above, right? To get f of 3 and f of 4. So we can put x equal to 2, which will relate f of 1, f of 2, and f of 3. So out of these three, if you know 2, you can find the third. So knowing f of 1 and f of 2, you can find f of. Next step, if you put x equal to f of 3, I will relate f of 2, f of 3, and f of 4. So now knowing f of 2 and f of 3, you can find f of 4, etc. So this kind of inductive chain can proceed. So and our what we want to prove is that f of q is q plus 1 by q. So therefore, by induction, we can prove that for all natural numbers, f of n is equal to n plus 1 by. And I will not do the calculations, but I think that you can take care of that, right? Just we already established the induction base. So in this case, the induction base had to be started with two values, not one value. So we need f of 1 and f of 2 both to start computing f of 3. And then after that, the whole chain can proceed. Okay, so we found the values for all natural numbers. But we would like to find a value for any rational number, right? So we still have, how can we reach from natural numbers to rational numbers now?
Sir, we know that it is true for if f of y is equal to f of 1 by y. So reciprocal thing is managed.
Yes, correct. So we can find for all f of 1 by n for all n, correct? And then what can we do?
Now we can again plus add 1, like, because
But the difficulty is that here we need three values, right? F of minus 1 plus, if it were that f of x and f of x plus 1 is related directly, then we are done. But here that doesn't seem to be the case. So to get that sort of induction chain started, right? We need two values, not one. And not only that, the jump that the equation 2 gives us is of size 1. So f of 1 by n and f of n plus 1 by n can be related like that. But f of 1 by n and f of 2 by n cannot be related in this way, correct?
yes, sir.
But what else can we do?
Sir, in the first equation,
Hmm.
if we replace x is equal to 1 by n
Okay.
and y is equal to 2, then we get that f of 1 by n times f
Hmm.
of 2 is equal to f of 2 by n plus
Yes,
plus f of 2n.
correct.
So
So just continue thinking on those lines. Do you see that not just f of 2 by n, any rational number can be reached that way?
Yes.
because basically we have conquered the natural numbers now. So in this first equation, x and y can be set to any natural numbers, right? Any p and q you choose, right? So let np and q be any natural numbers. And if I substitute p and q in the first equation, the equation I'm getting is f of p, f of q is equal to f of pq plus f of p by q. And now out of all of these, three terms are already natural numbers, p, q, and pq. So their values I know. So therefore, we directly know f of p by q now, right? And let's just do that calculation here. So basically, f of p by q will be equal to f of p, f of q minus f of p. And now assuming that we already proved that this is equal to p plus 1 by p. Okay. So if you just open this out and rearrange, you will see that basically everything is gets cancelled and I'll be left with p by q plus q by p. So which implies that f of p by q is equal to, I mean, this also satisfies the same relation. F of x is equal to x plus 1 by x for all positive rationals. Okay, I hope everybody is following this, that how from natural numbers going to all the rational numbers was just one step by substituting in the equation 1. Notice how, again, see, notice the structure, the exact details, whether it's multiply or add is not important. See, in the first equation, instead of f of x into f of y, if it were f of x plus f of y also doesn't matter. What is important is which variables are being related. So three integers and one non-integer is being related. So that structure is what we need to pay close attention. Okay, so with that, I would like to give you a few practice problems from past info papers, and that is how we'll continue to sort of develop whatever theory is required to problem solving practice. Okay. So maybe first equation for you to try. So now, as I said that I would like to take all the questions from actual INMO papers because that is the best sort of reference material. So I think this is from INMO 2001 question 6. So find okay, x plus f of x plus y is equal to f of x f of y into f of x y for all real numbers. So this is the function going from reals to reals. I'm deliberately starting from the older INMO papers because I don't want to sort of spoil the latest question papers. If you want to practice them in like a proper INMO time format, so would like to keep the at least the last 5 years papers reserved in that way that you can solve them independently. This is question 1. Question 2 is from INMO 2005. Okay, fine.
Sir, in the second question, it is f of x square.
F of x square, yes, f of x square plus y times f of z is equal to x f of x plus z f of y. And question 3, I'll just write it here actually, and I've not got a chance to attempt it, but might be a good one. So it's actually from IMO shortlist 2018 A1. To find all.
That's x square into f square of y.
X square into f square y is equal to f square x f of y. Let me just make one comment about this notation, which I don't really like, but it has sort of become commonplace, writing f square of y, because you know what this is really saying as f of y whole square. Okay? Instead of writing f of whole y whole square, they are writing f square of y. But there is a different context in which f square of y can mean something a bit different. It can mean applying the function f two times. So f of y, like that kind of a thing can also be called f square y. But I mean, this kind of confusion will happen if you are reading textbooks. But at least in more any problems you are doing, the assumption is that this is the version that they're talking. I mean, this is what we do in trigonometry also, right? We write sine square x, which is not sine of x, it is sine of x whole square. Okay, so just keep that in mind. And here q plus is the set of all positive rational numbers. Okay, but anyway, we'll start with the first problem. So I'll give you some more time to think. Okay, so how do we get started with this?
Y equals to 0, we can substitute.
Yes, f of x plus y x.
We get f of 0 to be 1.
Wait, y equal to 0, so f of x is equal to f of x times f of 0 square. So now what will happen?
F of 0 square equals to 1, so f of 0 equals to
Right.
plus minus
But
1.
before we do that, how do we know that we can cancel f of x from both
Sir,
sides?
if f of x equal to 0 for all x belong to R, that's one solution.
Right. Okay. So yeah, basically, looking at the equation itself, we can see that f of x equal to 0 for all x is already one valid solution. So that let us consider the other case, that suppose if this is not the function we are considering, so then in that case there exists some x such that f of x is non-zero, and if you use that value of x in this equation, then that gives us the right to cancel f of x from both sides. Okay, and therefore 1 is equal to f of 0. So yeah, I mean, this is a very small detail, but important to pay attention to that. Okay, so f of 0 square is 1. But
F of 0 is plus minus 1.
f of 0 is plus 1 or minus 1. Okay, so at this point, we don't know which of the two values f of 0 will take. What else can we find out from the
I
original?
think I'm able to calculate for natural numbers in terms of 1,
Okay,
in terms of f of 1.
okay,
Like if we put y is equal to 1, we get f of x plus 1
y is equal to 1, with f of x plus 1 is equal
equal
to
to f of x square
into f of
f
1.
of 1. Yes, so if we put now x is equal to 1, you get f of 2 is equal to f of 1 whole cube.
Yes, correct. So this equation is clearly relating f of x and f of x plus 1. So basically, from f of 0, you can relate f of 1 and f
No, sir,
of 2.
actually we can't do that. From f of 0, we can't get f of 1 because the f of 0 whole square is just 1. So that gets cancelled. We get f of 1 equals f of 1.
Oh, interesting.
We can relate from f of 1 to f of 2, then and
Okay,
so on.
I see. Okay. So from f of, so we have to probably assume some value of f of 1, and from that f of 2, f of 3, all natural numbers can be reached this way. Okay. But one important thing to understand is that we are talking about real numbers, right? So our sort of, at least the intuition of rational numbers is that we build step by step. We first find natural numbers, maybe then we find negative numbers, and then we find rational numbers. That cannot extend to real numbers, because of course we have irrational numbers and what are called transcendental numbers like pi and e. So the question asks you to find the value of even f of pi and f of e, and there is no way to do like this kind of systematic step by step way to reach that arbitrary value. So this information about natural numbers will be useful for our intuition to guess what the function can be, but it will not be enough to prove the value of the function for any arbitrarily real number. So that is something that we have to keep in mind. So I mean, the whole approach for real numbers is very different from rational numbers. But anyway, let's continue and see what more information we can sort of pull out of this given information.
So sir, in this approach, I got that f of 2, like f of 2 is f of 1 cube, and for f of 3, you just multiply the exponent of 2 and add 1. So
Okay.
hence
So
I
what
will,
what did you get for f of n in general, or
I'm yet to calculate that, but I got f,
okay,
like for the next step, you just multiply the exponent by 2 and add 1.
right, correct. Yeah, yeah, makes sense. So one idea which we always try to do is that if we have f of 0, actually we don't even have f of 0, but it's either plus 1 or minus 1. So we have to think about how can we force any of the given terms to be 0 or 1. So for example, in this expression, you can try to see how x plus y can be made to be 0. So if I put y equal to minus x, so I'll get f of 0 is equal to f of x f of minus x into f of minus x square. Okay. So f of x, f of minus x, and f of minus x square, they are going to be related in some way. So one more interesting observation that you can look at is, see, f of x plus y is something times f of xy. Okay. So let me just write it that way. X plus y is equal to something, doesn't matter what that is, times f of xy. So suppose we know, let there be some k, okay, such that f of k equal to 0. Okay. Suppose some such k exists, okay, such that f of k is equal to 0. If such a k exists, in this expression, can we make xy equal to k in some way? Okay. Suppose xy can be forced to be k. So if you choose some values of x and y such that xy is equal to k, then that will mean f of x plus y is 0, right? Because f of x plus y is equal to something times f of xy, which is equal to 0. And how many such xy can exist whose product is equal to k?
Infinite.
Infinite. And for each of those values of xy, there will be some value of x plus y, right, corresponding. So which means that we have shown that if f of f is 0 at some one point, it can be shown to be 0 at infinitely many other points. Do you see that connection?
Yes, sir, but not for all real numbers, right?
Yeah, that now depends on what is the possible range of this x plus y expression. So that you can try to think about, like, as xy is equal to k is satisfied, what is the entire set of real numbers which x plus y can span? But even if we don't get the value for all real numbers, it's definitely we are going to get it for a significantly large portion of the real number line, right? Of course, all of this is based on the assumption that such a k exists, that if there is some k such that f of k is 0, then all of this happens. There is no guarantee that such a f k might exist also, but that is what we can think about.
Then I think if k is equal to f of k is equal to 0, then we can show that for all real numbers between minus of 2 root k to plus of 2 root k are 0.
Minus of 2k plus of 2k.
Because then x plus y is equal to t and xy is equal to k should have a common solution.
Yes.
So I got that quadratic.
Yes,
That u square minus tu plus k is equal to 0 should have a real root.
yes,
So t square minus 4k is greater than or equal to 0.
right.
And that's why t should belong to the uh, like it should t square should be greater than or equal to 4k.
Right. So then in fact that is a infinitely large, it's not a
Yes.
finite range, right?
So
It's an
minus
infinite.
infinity to minus 2 root k,
Yes,
comma 2 plus 2 root k to plus infinity.
yes, correct. So if just to proceed along what Arnav said just now, so maybe let's call this x plus y is alpha and x y equal to k. So the equation you're looking at t square minus alpha t plus k is equal to 0. This should have real roots. So therefore the discriminant alpha square minus 4k should be non-negative. So therefore alpha square should be greater than 4k. So therefore alpha basically now this interestingly depends on if you see what is the value of k. Suppose k is negative, then do you see we are done?
Yes,
If,
sir.
if k is negative, it means because then alpha square can be any non-negative value, and then that means alpha can be any real number that we want. So if we happen to find a negative number where f of k is 0, then we are done. Of course, all of that is based on that assumption that we find such a value. But I mean, for example, we were looking at f of 1 and f of minus 1 earlier. So I don't know. Can you think what f of minus 1 could have any role to play in this approach?
Sir, we are able to relate f of 0, f of 1, and f of minus 1.
Sorry, can you repeat that?
We are able to relate f of 0, f of 1, and f of minus 1.
Okay, how?
From the equation we got above, that f of 0 equal f of x into f of minus x into f of minus x square.
Yes, yes, correct. By the way, one important thing to realize, if you look at the function, right? See, we are still in the two minds. We don't know whether f of 0 is 1 or minus 1. But can we make this assumption that without loss of generality, let f of 0 be equal to 1? Do you see why we can make this assumption?
Yes, sir, because if not, then we can define another function g of x as minus of f of x, and then it holds
Yeah,
for
correct.
this thing.
So see, important thing is that here there is one term on the left side and three terms on the right side. So the number of terms is odd, which means if I just multiply everything by minus 1, I mean the equation will still remain valid. So if basically if f of x is a valid solution, then g of x, which is minus of f of x, is also a valid solution. Okay. So therefore, I can just consider basically the solutions will always occur in pairs like this, where one is the negative of the other. So I can consider if I'm dealing with the member of that pair where f of 0 is positive. So I can say without loss of generality, f of 0 is equal to 1. Okay. So at least now we can fix the value of f of 0. And now, as what Arnav said, this equation, what it gives us is that this equation, right? That f of 1, f of 0, which is 1, is equal to f of 1, f of minus 1 whole square. Okay.
Sir, actually, in our previous thing of f of k is equal to 0,
Yes.
if we get actually if we can find any k, that would imply that all are 0, because we can just input k, x is equal to k, so we get
Okay.
that f of k plus y is equal to 0. So y can take any value, so we get that all real numbers satisfy are 0.
Oh yeah, yeah. Sorry. Actually, you are correct. I missed that completely. Yes. So did everybody follow what Arnav said? That basically I was looking at how f of x plus y is related to f of xy, but there is I sort of did this intermediate terms as dot dot dot, but actually those are the important part. So I can also say that f of x plus y is equal to f of y times something else, doesn't matter what. So now do you see here clearly we have a case where this f of y can be fixed and f of x plus y can be variable. So every value of x I choose, I'll get a different value of x plus y. And if let's say I want to find some value at z, okay, so if I want to find f of z, so I can force f of x plus y to be equal to this by choosing x is equal to z minus y. So if I choose x equal to z minus y in this equation, I'll get f of z is equal to something, and there f of y, if we have chosen such that that is equal to 0, then f of z equal to 0. So therefore, what it means that if the function is 0 at one point, it is 0 everywhere. Okay, that is what this
Yes, sir.
implies.
So that was our first case, that f of n is equal to 0 for all n.
Yes,
So
but
if we go for the other one, that f of 0 is plus minus 1, then we can say that f of k is not equal to 0 for any k.
yeah, correct. So if it is not 0 at any one point, it is never 0. That is the sort of other side of it, right? So now we are safely can assume that not only there, here we said let there exist a x such that f of x is not 0. Now we can claim the more bold thing that for all x in R, f of x is non-zero. So let us proceed by f of, so 1 is equal to f of x, f of minus x, f of minus x square. So this is one piece of information that we obtained. What else can we obtain from the original equation? F of x plus y equal to f of x, f of y, f of x, y. So one idea is that why don't we try to create the value of x on the left hand side? So instead of here x plus y, x f of x is on the RHS and f of x plus y is on the LHS. Can we choose some value of x and y such that f of x can come on the LHS? So in other words, can I think of two values to substitute here? So for example, x is equal to, I can choose both of them to be half and half, like x by 2 and x by 2. Another idea is that I can choose x to be 1 and y is equal to x minus 1. Okay. So what happens if I substitute x is 1 and y is x minus 1? So I'll get f of x on the LHS is equal to f of 1, f of x minus 1, and f of x minus 1 again. So I mean, this is something that we saw earlier also. F of x and f of x minus 1 can be related in this way. So and we had a very similar equation earlier also, right? F of x plus 1 is equal to f of 1 times f of x square. So basically it's the same thing in a different way. So I mean, can we see some connection between this expression that we have, f of x, f of minus x, f of minus x square, and this kind of equations? in particular, this part, right, f of x minus 1, you see f of x minus 1 can also be, it's a function and into, you see this has the same form as this, f of x minus 1 and f of x plus y, they have the same form. So I can apply the same f of x plus y once more over here. So what can I write f of x minus 1 as? It is f of x, f of minus 1 into f of x into minus 1, right? So f of minus 6. So now do you see that there are some things which can come out common or get cancelled? So I'll get f of x is equal to f of 1 times f of x, f of minus 1, f of minus 6. Whole thing twice. So I'll get f of x, f of minus 1. And now because we are working with the assumption that function is non-zero at all points, so I can safely cancel f of x from both sides. And what will I get? So 1 is equal to f of 1 times.
And f of 1 into f of minus 1 square is also 1.
Yes, correct. So in fact, we can drop that term entirely. So we'll get f of x into f of minus 6 into f of minus 6 whole equal to 1. So this part can be dropped. So therefore, f of x into f of minus x whole square is equal to 1. So now notice the slight asymmetry that f of x is occurring once and f of minus x is occurring twice. So how can we exploit that asymmetry?
We can put now x equal to minus x.
Yes, correct. So if I just change x to minus x, then we are also saying that f of minus x into f of x is equal to 1. So equating these two, and again we are able to cancel terms which are on non-zero. Do we see f of x is equal to f of minus x? Okay. So this is actually a very important step because what we are showing is that f is an even function. So this is what is called an even function because in a way it's kind of symmetric around the y-axis if you draw the graph. So we are almost done actually, because now if you think about it, the fact that f of x and f of minus x are equal in this expression, what does that mean?
So sir, in the above equation, we get that 1 is equal to
Hmm.
f of x square into
Hmm.
f of minus x square. And of f of x square and f of minus x square are equal. No, they're
No,
not
no,
equal.
no,
It's
no, wait,
x
wait.
whole square. Yeah.
Why are you getting f of x square?
No, f of x whole square actually. F of x whole square into f of minus x square.
No, sorry, which equation are you referring to?
The upper one. Can you scroll up a bit? Yeah, that one, the red one.
This one?
Above that, the underlined one.
Okay, okay.
Yeah. So that's 1 is equal to f of x whole square into f of minus x square.
Yes, correct. Yeah, you can do from there also because what we'll get is 1 is equal to f of x whole square into f of minus x square. And now because we know it is an even function, so I can drop the minus sign. So it's f of x square into f of the x square inside. And now we also have an equation from earlier where f of x square can be related to f of x, right? So I can substitute that over here. And what will I get? So we had earlier derived.
No, sir, actually, I think the relation between x square and x was for the previous problem, not this one.
Oh, sorry, I got mistaken. Yeah, but actually, I was not even referring to that equation. I'm talking about this equation. In this one itself, because f of x and f of minus x are equal now, what does it mean?
Oh, that's f of x whole cubed.
Yeah, exactly. So f of x whole cube equal to 1. So therefore, f of x is supposed to be 1 for all x. Okay. So I mean, in the end, this turned out to be kind of easy problem to finish, but there was only one important step, which is, so this is what I mean by when I said, consider something, that consider solve the problem for us. That was this step from f of x plus y, substituting. Basically, we already had this equation, right? F of x plus 1 is equal to f of 1 into f of x whole square. But what we didn't think about was just taking this equation down by one level. So instead of talking about x and x plus 1, the same equation could be referring to x minus 1 and x. And then what that allows is that on the RHS, x became f of x minus 1, which allows us to apply our given function equation information once more to split this and everything. So that was the sort of sudden jump which helped us to solve the problem. Okay, so finally, what is the solution set? So all of this was done with the assumption that f of 0 is equal to 1. So instead of that, if you consider f of 0 equal to minus 1, then you will obtain a similar equation answer that f of x equal to minus 1 for all x. So basically, there are three solutions. Either f of x is 0, is minus 1, or plus 1. And there cannot be any other solution, because we are basically everything is forced to be a one-way state, that if f satisfies something, then through the chain of logical reasoning, we are forced that f of x cube is equal to 1. Okay, so this is a very good problem for INMO, because it doesn't demand any advanced theory or knowledge, just being clever about substituting the right values in the given equation. That is the real sort of idea. Nothing else is involved. Okay, so the more practice you do of these kind of problems, you will get better and better at thinking various ideas of what substitutions can be done. But the important thing is you have to keep in mind, because this example here you will forget after a few weeks or months. So how do you keep track of what are the various substitutions that you can attempt, and try to create your own sort of toolkit, right, of various techniques that you can use in any given problem. And as and how you solve more and more problems, try to relate those new problems to the toolkit that you already have. That which tool are you able to use effectively, or if you may encounter a new problem which you cannot solve with the tools that you already have, then when you read the solution of that problem, you should add that tool to your arsenal. Okay? So should keep expanding your the sort of ideas that way. Okay, so we can move on to question 2. So a question like this is a double-edged sword in the sense that in a way it seems that x, y, z, there are three unknown variables. So which means that you have so much freedom to substitute so many values and you get so much rich information about the function. But that also comes with the risk that there is too many substitutions that can be done, and out of those, just finding the right substitution which will solve the problem can appear challenging. So sometimes it's good when you don't have a lot of options, because that well-known phrase that if you have a hammer, everything looks like a nail. So if you had only one tool available, then you just apply that tool, and that is the only thing you can do. But here we have so many options available that what value you choose for X, for Y, for Z. There's too much information that can be generated. So we need some like systematic way of thinking about what is the information we are interested to obtain, and then to reach that goal, we'll substitute the X, Y, Z accordingly. So that is something that we need to keep in mind while solving a problem like this. So f of x square plus y f of z.
Sir, I got that f of x square is equal to x times f of x, and so f of 0 is equal to 0.
Yes, correct.
And also I got one more thing, that f of x square, f of in the bracket x square plus f of x square is equal to 2x times f of x.
Okay. How did you get the second expression?
Sir, y is equal to z is equal to x we put, and then use the first equation.
All right. Okay, got it. So, I mean, we'll obviously start with the usual idea that we want to put the variables as 0. But important thing I want to indicate: don't put all of them as 0 at once, because then you might lose information. Okay, so put the variable 0 one at a time. So let's just put z equal to 0. Okay. So if I just put z equal to 0, I'll get f of x square plus y times f of 0 is equal to x f of x. So at first this looks like a very promising equation, because it has a structure where RHS doesn't have y, only LHS has y. So the feeling is that if I change y, I can change the LHS to be any value I want and force the function to be constant. Of course, that whole depends on whether f of 0 is non-zero. But as soon as you do the next substitution, you realize that unfortunately f of 0 is 0. So it's not that useful. But still, I mean, just the way you think about it, that obtaining the separable variables that way can be useful in some context. Okay, so f of 0 is 0 and f of x square is equal to x times f of x. And now, Arnav, can you repeat the substitution? I think you said y equal to f of z, or what was the idea?
Sir, y is equal to z is equal to x.
Y is equal to z. Okay, so again, let's just put y equal to z first and see what that gives. So that gives f of x square plus z times f of z is equal to x f of a plus let me put everything in terms of y. No, y times f of y. So actually, do you see this is almost like a additive kind of function, because we already know x f of x is nothing but f of x square. So it's looking very close to some kind of additive expression. Now in this, if you put x also equal to y, then we get f of y square plus y times f of y is equal to y f of y 2 times. Okay. Also want to point out very important technical or structural difference between this functional equation and the previous one, and that is what we can call the presence or absence of free variables. So free variable means a variable which is not enclosed by the function itself. So in a way, so here you see this x and z are sort of bare variables outside the function bracket, which the previous equation did not have, right? If you look at the previous one, f of x plus y is equal to f of x, f of y, f of x, y. So there x and y were all enclosed inside the function itself. So see, starting from an equation like this, you see that in principle, no matter what manipulation you do, it's very hard to end up with the expression like f of x equal to some x or x plus 1, or doesn't matter what. You cannot pull out that variable x out of the function bracket, no matter what you do. So this kind of a nice solution was not expected anyway for the previous problem. Whereas for this problem, we can expect some solutions like this, where f of x can be directly expressed in terms of x. So, understand the difference between the structure of the functional equation, and that will indicate what guesswork you can make. So, in the previous question, it was not really a good idea to guess a expression like this, but here we can try to guess. So, any ideas to guess before we try to solve that what the function can be?
Sir, f of x
Here.
equal to x works.
F of x equal to x works. What else can work? See, f of x equal to 0 also works, because
Yes.
f is occurring everywhere. So this is clearly a solution. F of x equal to x for all x seems to work. And soon we'll see one more thing. So again, continuing, we know f of 0 equal to 0. So try to think of what parts of the original equation can be forced to be 0. So how about if you here see, look at the order. We first put z equal to 0, then y equal to 0, then x equal to 0. So by the time we put x equal to 0, y and z were already 0. But what if we reverse the order? What if we put x equal to 0 first? Then what will the equation give us?
F of y times f of z is equal to z times f of y.
Okay. So this is a very interesting function, because applying the function seems to reverse the order of f. So y f of z becomes z f of y. Okay, a very interesting operation. And now see, because we already know that f of x equal to 0 is a solution, so we can safely assume that let f be non-zero at some point. Okay, so we can say that there exists some k such that f of k is non-zero. That can be safely assumed. So now if you see the expression y f of z, you see that by changing the value of y, I can force this to be any real number. So for any real number t in R, I can choose y is equal to t upon f of k, and I choose z is equal to k. If I make this choice, you see that this y f of z will be equal to t. Okay. So what is the point of doing this? So by the way, here again, notice how there is a slight asymmetry between y and z. So how can we exploit that asymmetry?
Sir, how did we assume that let there exist a case such that f of k is not equal to 0?
Because we already have observed that f of k identically 0 is a solution. So without loss of, we can say we are looking at the other case, where
Okay.
we are talking about a function which is not 0 everywhere.
Okay, sir. Yes.
Okay. So in this given expression, right, f of z equal to z f of y, do you see that by reversing the position of z and y, we can also obtain another equation that f of z f of y is equal to y f of z. So putting both of these things together, what we are saying is f of y f of z is equal to y f of z. And now with this particular substitution, I can make y f of z equal to any real number. So therefore, in fact, what I can say is that f of x is equal to x for all x. Okay, did you follow the last few steps? So first was just reversing y and z in this equation to get a new equation. So now you see what was inside the bracket previously. Y f of z is now outside the bracket, and what was outside the bracket is now inside the bracket. So this is like a reflection operation, that applying the function takes you to new value, and applying the function to the new value brings you back to the original value. So there is a special name for a function like this. They are called involution. So an involution is any function which you apply twice, you come back to your starting point. So an example of involution is of course minus x. Okay. So f of x equal to minus x is a involution.
Sir, what was the use of that t?
I mean, see, in this expression, we didn't know whether, I mean, this statement is true for all y and z. But from here to jump to the conclusion that for every real number x, it is true, that is conditioned upon whether this expression y of z can take all real values or not.
Okay,
And
yes, sir.
to achieve that, we chose like knowing the fact that there is some f of k which is non-zero. So basically, f of z can be forced to be constant, and y can be varied through all numbers. Basically, same thing that you did in the previous question, right? Where x plus y, we keep y constant and we vary x.
Yes, sir.
So we are getting a lot of useful information about the function. And we have made the guess that f of x equal to x, but we still have not proved that. So what else can we do in this question? One more thing that we can observe from this information, f of x square equal to x f of x. You see that instead of x, if I take minus x, of course f of x square will remain the same. So what this means is this is also equal to minus x times f of minus x. So do you see that f is what we call an odd function? Because basically what this gives is that minus of f of x is equal to f of minus. Okay? For all real numbers x. So x is an odd function. So x is an odd function, x is an evolution. Yeah, we are getting a lot of sort of the pieces of the puzzle, but we have to put all of that together. So we know f of x minus f of x is equal to f of minus x, and f of x is equal to x. And now obviously the original equation that we had. Okay. So there is one more implication of this involution operation. And this is true for any involution. Suppose, so let there be two numbers a and b, such that f of a equal to f of b. Then what can you say?
A is equal to B.
Yes, correct. So what does that mean? What is f?
Strictly increasing or strictly decreasing.
No, not necessarily, but do you see that means f is a 1-1 function?
Oh, yes, sir.
Okay. So if we apply f to both sides, so f of a is equal to f of b. And now because of the involution property, this is simply saying a equal to b. So basically in terms of the picture that you can draw, if you have 2 points a and b whose output is the same, then the 2 points themselves have to be the same. That is what we mean by 1-1 function, that there cannot be any value in the RHS which is taken by more than one value from the LHS. So f is also 1-1. And I'm pointing out all of these things because quite possibly in the exam, even if you don't get the full problem, finding all of these properties that f is an odd function, involution, f is 1, each of them will carry some partial marks because all of them will be relevant in the final solution. So like whatever like intermediate observations you are able to find like this, all of them are used. Okay, f is 1. Can we see whether f can be onto also? So what is onto mean that for every value of x, there exists some there has to exist some y such that f of y is equal to x. So does such a y exist for every value of x?
Yes, we take y is equal to f of x.
Yeah, exactly, right here. So that is what involution gives. So basically, in other words, every involution is a bijection. That's a very important thing that we are discovering. So every involution is a bijection because it is 1 and also onto. So we have so much information about the function, but we still don't know what that function is. So now just observe one thing. You see we wrote this expression f of y f of z equal to z f of y. In a way, it was like we are able to get rid of one copy of f, right? On the LHS, we have two invocations of the function, and on the RHS, we have only one invocation of the function. So it is like exactly what we want. Because ultimately, suppose you want to prove that f of x equal to x. Okay. So we want to end up with a situation where f is occurring once on the LHS, but not occurring on the RHS. So this kind of asymmetry of the number of times function occurs on both sides is important for us. And that is being achieved through this f of y f of z is equal to z f of y. So this equation will be very important for us in that way. So now, for example, just consider substituting y and z to be equal. So f of z f of z. Can I say this f of z f of z equal to z f of z? Now, only thing if same as what we did earlier, right? This part z f of z, if we can show somehow that this can be forced to be any real number, then do you see that this implies f of x equal to x for all x?
Yes, sir.
Yeah. So now the only question is that true? That can we see why z f of z can be forced to be any real number we want? So for example, if I want to find, suppose I want to find some t which is a real number, I want to find f of t. So how can I find the value of z such that z f of z is equal to t? So does such a z exist? That is what we would like to know. So to find such a z such that z times f of z equal to t, notice that we already have this expression. F of x square is equal to x f of x. So in other words, f of z square is equal to z f of z. So the question of whether we can make z f of z equal to t is the same as the question of can we make f of z square equal to t. And we know f is on 2, right? So there exists some, there will exist some real number, if I call it, I don't know, m, such that f of m is equal to t. And now if that m is non-negative, then I can write m is equal to z square, right? And if m is negative, then
f of minus m is f of m. Oh no, it's negative of m.
negative. Oh, sorry. Actually, I made a mistake. Then. I thought that was the. I also assumed f of m equal to f of minus m. Okay, so then there is a difficulty here. How do we solve that problem? But I think we can solve the problem in this way that we know that f is an odd function. So we know, I mean, it's enough to find the values for only positive or only negative values, and the other will be implied. So what we can do is there exists a m such that f of m is equal to t. Now, if let's say m, if m is greater than 0, then we are done because that will imply like root of m, radical of m can be said to be z, and basically what will that imply? That f of t is equal to t from this, whatever we did above. And now if the reverse is true, let's say m is less than 0. Okay, now we just consider the instead of t, we'll consider minus t, right? So we'll prove that f of minus t is equal to minus t, and from there we'll get f of t. So instead of t, we can just consider the complement of t, minus t. Can that work?
Well, what you are saying is that we prove for positive values.
Yes. And then we, because the f is given to be an odd function, that will imply the value for negative. We don't have to do that separately. Yeah, I'm not very sure about my argument, but I'm just.
So like, what did you do if m is less than 0?
If m is less than 0, then what I'm saying is
F of minus m is minus t.
yes, f of minus m is minus t, exactly. So f of minus m is equal to minus t, and now minus m can be written as square root of minus m will be a number, right? So z can be said to be square root of minus m. So therefore, what I'll get is f of z square is equal to minus t, and now f of z square is nothing but z f of z. So z f of z is equal to minus t. And now in this, basically substituting z f of z in this expression, what I'm saying is f of minus t is equal to minus t. And so once f of minus t is equal to minus t, then knowing that f is an odd function, it will imply that f of t is equal to. Yeah, that should work, right?
Yes, sir.
Yeah. Okay.
Sir, also in the above equation, below that red line, find t belong to R. Below that, f of z square is equal to z f of z.
Yes. Yes.
So that was the thing we have already proved it.
Yes. So yeah, we are using it here. So we want to find the t such that f of t sorry.
And then We want to
No,
find t such that f of z square is equal to t, right?
no. See, what I know is, let me just back up. This is the expression that I know. This is true for all values of z. And so this is of the form f of something equal to something. So in that, this zf of z is the expression. If zf of z can be forced to be any real number I want, then I'm done. So let us say you choose any real number t, and you want to find f of t. So find sorry. So let t be any real number, and I am interested in computing f of t. And to compute f of t, I would like to uh, adjust things such that t is equal to z f of z for some z. Okay. If such a z exists, then I can substitute z f of z over here, and basically this equation will become nothing but f of t is equal to t. So can such a z exist such that z f of z is equal to t?
So sir, t is equal to f of z square, right?
T is equal to f of z square.
Okay,
Exactly.
yes, sir. Now
Yeah.
now it's right. Yeah.
So t equal to f of z square. And now the question is that because f is given to be an onto function, or rather we have found f to be an onto function, such a f z square will exist, or rather some m will exist. So there will exist some m such that f of m is equal to t. And now that if m is positive, then m can be directly set to z square, and if m is negative, then the second part that we did below. Okay, so yeah, this was kind of a long problem, but effectively the lengthy part was just the exploration. So all of these things you'll do in the rough work. Finally, what you'll write in the solution is just the parts which are important. So there could be a lot of side discoveries that we'll make, which are not useful for our problem anyway. So we can ignore those and just write the part which is uh, helping us to solve the problem. Okay. So, by the way, this is just one solution. There can be other solutions also. Let me just check the official solutions because there could be some other approach they have indicated. Okay, so I think official solution also is finding the same equations as us. So f of x square equal to x f of x, and f of y f of z equal to z f of y. And I think after that they are doing something different. So now they are saying put y equal to 1 over here. So we'll get f of z is equal to z times f of 1. Okay. How does that help us? And now in this expression f of x will equal to x f of x. If we just apply the function to both sides, so we get f of x square is equal to f of x times f of x. Okay. Okay. And now because of this, basically I can pull the z out. If I f of z, then z can be pulled out straight away. So therefore, so this part can be replaced by simply x square f of 1, and the right hand side f of x f x. So here basically from this equation you see that I can cancel the f and directly write x in. And in this equation, if I put x as y equal to z, then I'll get f of x equal to x f of x. So therefore I can directly get this, and now at least for x non-zero I can cancel x and I'll get f of x is equal to x times f of. And then you can compute f of 1 in some way. So therefore this is the, so therefore this implies that f of x is equal to x. That was their solution. So yeah, I think up to the second last step, both solutions were together. But then we were looking at how to use the f being 1, 1 and on 2, whereas they found a direct way to find it. Yeah, I mean, if you can think of this solution, this is definitely much shorter solution. But always the question is that how should you think of, particularly putting y equal to 1 was an important step here that we didn't think of actually. So that was help to find the solution. So appreciate the pros and cons of both solutions. The solution that we chose, I would say, was more systematic in the sense that we knew what could be used at every stage. So finding that f is an involution implies that f is a bijection, that is, it is 1, 1 and on 2. And in particular, obtaining this expression that f of something equal to something, that kind of expression. And then the thing which is inside the bracket, can we force it to be all real numbers? So that was the pattern that we followed. Okay. And there could be one more solution also. I mean, probably if you Google it, you will find more solutions of this kind. So there is one more third question, but actually I will not be able to solve it today. But I'll encourage you to attempt that third question also. Yeah. So this shortlist problem, even I have not attempted that, so it will take me some time to first try it out. But hopefully, again, just looking at the problem, do you see it is a very sort of multiplicative nature of the question, that there is no addition involved at all. It's just product of numbers, that kind of a question. So try to approach it that way. And so because we have, as I said, maybe 5 or 6 lectures before actual INMO, at least what I'm going to try to do is we'll pick a theme every time and we'll solve a few examples of that theme. So for example, today we will do functional equations. Then sometime we will do some combinatory geometry, some number theory or inequalities. So like that, one at a time, we'll just explore one theme and try to show how what are the various problem solving techniques required to solve problems of that kind. And apart from that, I will encourage you to, so I mean, throughout what I'll try to do is I'll avoid solving the latest 5 years papers. Okay. So in more 2016 onwards, these papers are available to you to solve independently. Okay. And so that will give you sort of more systematic practice of solving all the 6 questions of a variety of topics. And I will cover all the papers before that in this kind of randomized way, covering one theme at a time. So that is how we can structure your next few weeks of study. And any problems you are solving, any question papers you are solving, you can always send me your solutions. I'll check those and give you some feedback. In addition, I think there will also be a training camp in Pratishthan. I don't know the exact dates, but most probably they will get decided in the coming week or so. So there again, most likely I will also be there, so we can meet in person and study a few topics in that 1 week training camp. Okay, I think that's all for today. So I'll decide which is the topic for next week, and I will same as what we are doing before, right? I will tell you which problems we are going to solve in advance so that you can come prepared with your own attempt of those particular problems. So we'll save some time in the actual class and hopefully cover more problems. Okay, that's all from me. Thank you.
So the INMOTC will be conducted for this year also.
Yes, the camp will be conducted for sure, but the exact dates and schedule is yet to be finalized. So, I mean, as you may know, I'm no longer the coordinator of Maharashtra region. So, the current coordinator, Dr. Vikas Yadav, he will inform you about the schedule and everything. But I will be also in touch with him to understand the details.
So, sir, like, where will we come to know about the details?
When or where?
Where, sir? Where?
When? Maybe 3-4 days.
No, sir. Actually, like on site or something, will come to know about the details.
No, you'll get email. You'll directly be informed by email.
Okay, sir.
Yeah.
Yes, sir. Thank you, sir.
Okay. Thank you. Bye.